It's our honor to have Professor Garcia Elias from Spain. Thank you very much for accepting our invitation and coming to our Congress. And we are happy to have you with us. I hope you enjoyable stay in Luxor and in Egypt all over. So he will give us a talk about kinetic effect of axial loading in normal and scapholunate incompetent wrist. Please, Professor Garcia.
Salam alaikum. Thank you. It's really an honor. It's really an unprecedented situation for me. I do appreciate your thoughts and the fact that you asked me to come for this topic is something really unusual, and I like it. Thank you very much. Scapholunate dissociation is one of those pathologies that need to be always interpreted the way it is. As you can see, I've been interested on the kinetics of this articulation and this particular since long. This is myself. It was at the Mayo Clinic about 40 years ago. And still now I'm interested and pushed and interested about that. So let's go into the subject. The wrist is a complex joint. It's one of those articulations so much complicated. It comprises 15 bones, 24 ligaments, 24 tendons and joints and pulleys. It's really a complicated articulation. And why do we need such a complicated thing? Well, it's difficult to say, but to me, there is one reason in the fact or in the need to place the hand in a position that ensures effective gripping, but also to ensure proper transfer of loads from hand to arm. So it's mobility what we need, and we need also stability. And it's not the same. I mean, in other articulations could see the same, but in the hand, that's a key important issue. And that's why we are so much interested in the kinetics. Remember, kinematics is the part of the physics that studies motion, and kinetics is the part of the physics that starts interested on the forces. So, what's the role of the ligaments? Under load, bones move in specific directions. We all know that. Ligaments such as cables limit these movements within acceptable limits. And the acceptable limits may be the ones that we have in the radiocarpal joint, where the in that case, radiolunate ligament is a ligament that will stretch under axial loading and producing that ulnar translocation phenomena. Of course, if we have translation, we will have tension in the ligament and we will have more compression into the radiolunate joint. If there is more axial load, there will be more tension into the ligament and more compression in the joint. And that's going to be the case that we can have a crack. A crack meaning a rupture of the ligament. And the question is, does it mean also the fact that we have instability? If we have a torn ligament, we don't have instability. That's a fact. Why? Because if stability depended only on the ligaments, gymnasts all would have unstable wrists because the ligaments are not cables. We are saying always it's like a cable that holds a bone in place, but it's not true, because if it was, look at this. Ligaments are not cables, they are rigid but not that strong. The average tension inducing rupture of the scapholunate ligament is 360 newtons, which is 35 kilograms. And that's not enough to break the wrists of those gymnasts. So, we were interested in that, and we started thinking, how can we do to understand carpal kinetics, to investigate carpal kinetics? In fact, what we decided is to study the displacement to occur in the carpals and the different loading conditions. So it's not something that can be studied only in one direction. There is the whole of, and this is the essential wrist check that we have done at the University of Barcelona. Is a wrist check that helps us introduce an axial loading vertical, and you will see what happens. What happens is that if you go into the scaphoid will flexion always and pronate under the axial load, but the triquetrum will extend. There's no flexion, extension, and supination as well. So in a way, what we have is that scaphoid on the side pronates and flexes, and on the other side we have supination and extension. The more you rotate, the more compacted the towel becomes. So this will be a schematical representation of what we have. The axial load is imprinting that flexion pronation moment on one side and extension on the other. And everything slides down because this is not a flat surface, it is an inclined surface. That means that we have that extension, supination, flexion, pronation, opposition. Look at what happens. We have the force, axial force up there. And if you look at this specimen, you will see that the thumb is opposing palmally. That means that we have that ulnar translation and the lunate, and we have that flexion of the scaphoid. So now we know what happens is that flexion, that thing, and we can figure out what ligaments should be working on that. The ligaments, they all go around that circle, around the capitate, in a way that we could say that there's an antipronation system, a helical antipronation system, formed by several ligaments opposing to that ulnar deviation pronation. But as we have said, we need to also look at the forces in other ways. In that case, if instead of an axial traction, if we have an axial distraction, what we have it that the scaphoid extends, the triquetrum flexes, and the distal row supinates. And supinates, and everything is translated radially. That's exactly what we're expecting to have. And that's what we have found in those specimens. Now it's not the antipronation ligaments are signed the way it was. Now we have another type of reaction anti-scaphoid, and they are doing that anti-supination ligaments and suppose with the anti-pronation ligaments. So, those are the three types of reaction that we have in the wrist. We have hustle, meaning hustle high mid, anti-supination ligaments, and anti-pronation ligaments as well. Of course, as we have said, if we were relying only on ligaments, that wouldn't come. It comes because we have proprioception. And proprioception, you know that it's something that happens because the ligament, aside from having longitudinally oriented fibers, we have also mechanoreceptors. Those mechanoreceptors react producing some sort of reaction, the time latency, and then we have this, and we have the injury. And the more we do it, the more we realize that that's true. There we have, this is Elizabeth Haggard, our friend from the Karolinska Institute. She decided to stimulate one ligament and to see what happened into the forearm. And what he found was that there is a reaction. If there is a reaction by just opposing that stimulus on the ligament, if there is a reaction on the muscle, means that the muscles and the ligaments talk to each other. And they talk, and the way it is here we have the ligament held, and see how all this happens. And there we go. If you have realized, we have used two ligaments at the same time. The two ligaments, what we call that are synergistic. The two ligaments may well happen that one is ruptured, but the other ones are not. If we have that situation, we can accept that the reaction is the same. And that explains why we may have a rupture of the scapholunate ligament and nothing happens. Everything has to do with the time, and the muscles are called in. Why are muscles has to contract and others are inherent? How do muscles prevent carpal sagging if their contraction tends to compress the carpus? That was something that we wanted to investigate, and we did it by tendon loading. We used the same principle, but now we are just compressing the joint by means of forces applied to the tendons. Here was surprising to find that if you have a pronosupination intercarpal after isometric load, it was surprising. Surprising because, see, this is the tendon that we have loaded proximally, and the digital insertion of this. The ECU is dorsally located, and therefore the ECU will promote pronation to the carpal row. On the other side, if you have an anti-supination, ECRL and APL, we have the same. APL and ACR are strong supinators as opposed to the supination and pronation of the tendons. So here we have the case that we have come down to a solution to understand why we have that. The solution, if you see, is a cadaver with the scapholunate ligament rupture, and if we pull on the pronators, we are going to pronate distally, and we have that situation. And while if we have supinators, we have the contrary. So this is it. If we have a pronation torque, the muscles that will be called in are the supinator muscles, while if we have a supination torque, we have the pronator muscles as well as the ligaments. So, I finished a talk that it's extremely difficult to understand in less than 15 minutes. Thank you very much, my friend.